Right now, a piece of engineering negligence measuring less than 3 inches long is sitting in your Ford's exhaust manifold. It costs the manufacturer a fraction of a dollar at scale, and you can buy an aftermarket replacement for less than the price of a fast food meal. Yet, if you ignore this single component, it will trigger an uncontrolled thermal meltdown under your floorboards, transforming your catalytic converter into a solid block of fused ceramic glass. The factory maintenance schedule tells you to ignore it until a light pops up on your dash. That is a trap designed to walk you out of your powertrain warranty and directly into a $2,500 repair bill. When you buy a modern Ford, you are buying into an engine management ecosystem that operates on razor-thin margins of error. The manufacturer builds these systems to run at a chemically perfect stoichiometric ratio of 14.7 parts air to 1 part fuel. To maintain this delicate balance, the engine control module relies entirely on a tiny ceramic thimble coated in platinum. Known as the upstream oxygen sensor, this sensor is the sole guardian of your exhaust system. When it fails, the consequences are immediate, mechanical, and devastating. Manufacturers treat these sensors as lifetime components or 100,000-mile afterthought items. That is a massive mistake. The harsh environment of your exhaust stream, where temperatures routinely swing from ambient cold to 1,600 degrees Fahrenheit, degrades the sensor element from the very first start cycle. When you leave an aging sensor in your exhaust, you are playing Russian roulette with your engine's back pressure and your wallet. We are going to break down the exact sequence of destruction, counting down the hidden warning signs your truck is throwing at you right now. Sign number 4. The sluggish signal lag. Your engine control module modifies fuel delivery hundreds of times per minute based on instantaneous feedback. A healthy upstream O2 sensor generates a rapidly fluctuating voltage signal between 0.1 and 0.9 volts, switching multiple times per second. As the zirconium dioxide element inside the sensor degrades due to thermal cycling, its response time slows down. This creates a condition known as a lazy sensor. Instead of reporting exhaust composition in real time, the sensor lags by 2 to 3 seconds. Your engine management computer is now trying to adjust fuel trims using data that is already obsolete by the time it arrives. It completely misses every necessary fuel correction, leaving your engine running inherently rich during critical acceleration phases. The mechanical reality: a lazy sensor will not trigger a check engine light for thousands of miles, but it quietly overfuels your cylinders during every single drive cycle. The actionable fix: connect a $20 OBD2 Bluetooth scanner to your diagnostic port, open a live data app, and monitor the upstream O2 voltage graph at operating temperature. If the waveform takes more than 1 second to complete a full cycle from high to low voltage, replace the sensor immediately regardless of whether a fault code is present. Sign number 3. The 16 mpg drop-off. When the sensor element becomes completely blinded by exhaust soot or oil ash, it fails in a specific dangerous position. It gets stuck reading a permanent lean condition. It continuously sends a low voltage signal to the computer, falsely reporting that there is too much oxygen and not enough fuel in the exhaust stream. The engine control module reacts exactly how it was programmed to react. It lengthens the fuel injector pulse width, dumping massive amounts of extra fuel into the combustion chambers to counteract the phantom lean condition. Your vehicle's fuel economy will plummet instantly. If your F-150 normally achieves 22 miles per gallon on the highway and suddenly struggles to hit 16 miles per gallon, your truck is actively trying to destroy itself. You are not just wasting money at the pump. You are physically washing the cylinder walls with raw gasoline, diluting your engine oil, and sending unburned hydrocarbons down the pipe, the economic framing. Spending $15 on a proactive sensor replacement stops you from burning through an extra $40 of fuel every single week, while completely neutralizing a $2,500 converter replacement bill. The actionable fix: track your manual fuel mileage at every fill-up instead of relying on the dashboard display. If you see a sudden drop of 15% or more without a change in driving habits, pull the upstream oxygen sensors and inspect the tips for heavy carbon accumulation. Sign number 2. The rotten egg sulfur stencha rich engine mixture produces an unmistakable chemical byproduct when it hits your exhaust system. Under normal operation, the precious metals inside your catalytic converter, specifically platinum, palladium, and rhodium, catalyze harmful emissions into harmless carbon dioxide and water vapor. However, when a failed upstream sensor forces a flood of raw, unburned fuel into the exhaust, the converter becomes overloaded. The excess sulfur compounds present in standard gasoline are processed under extreme distress, creating high concentrations of hydrogen sulfide gas. This manifests as a pungent, distinct rotten egg smell emanating from the tailpipe. That smell is not an inconvenience. It is the physical sound of your catalytic converter screaming for help as its internal chemistry reaches its absolute limit, the mechanical reality. The presence of hydrogen sulfide indicates that your converter is no longer processing emissions efficiently because it is being suffocated by raw fuel. The actionable fix: walk to the rear of your vehicle while it is idling at operating temperature. If you detect a strong sulfur odor, park the vehicle, allow the exhaust to cool, and utilize an oxygen sensor socket to extract the upstream sensor for immediate replacement. Sign number 1. The 2500-degree internal fire. This is the final stage of the failure sequence before catastrophic component destruction. When raw fuel bypasses the combustion chamber due to incorrect sensor data, it does not simply vanish. It accumulates directly inside the dense ceramic honeycomb structure of your catalytic converter. Your converter is designed to trigger chemical reactions, not act as a secondary combustion chamber. But when that raw fuel hits the hot precious metals, it ignites inside the substrate itself. The normal operating temperature of a Ford converter tops out around 1,600 degrees Fahrenheit. When raw fuel ignites inside it, internal temperatures instantly spike past 2,500 degrees Fahrenheit. At this temperature, the ceramic honeycomb structure physically melts, collapsing the internal passages into a solid, fused block of glass-like material. This blocks your exhaust flow by up to 80%, building massive engine back pressure that can warp exhaust manifolds, blow head gaskets, and completely choke out your engine's power output. The cost comparison: a $15 preventive sensor replacement prevents a catastrophic meltdown that forces you to purchase a new converter, new downstream sensors, and potentially a new exhaust manifold, totaling well over $3,500 at standard shop rates. The actionable fix: if you experience a severe loss of engine power paired with a glowing red exhaust pipe under the vehicle, shut down the engine immediately. Do not attempt to drive the vehicle until you have replaced the faulty upstream sensor and verified the physical integrity of the converter core. Most vehicle owners assume that as long as the truck moves, everything under the hood is operating perfectly. They see a check engine light, assume it is just an emissions glitch that does not affect drivability, and keep driving for months. They do not realize that the engine control module has defaulted to a rich, protective fuel map that is actively cooking the vehicle's most expensive exhaust component from the inside out. And if you think a melted converter is the worst thing this tiny sensor can do to your truck when it goes bad, you are completely misjudging how deep this engineering flaw actually goes. The destruction does not stop at a melted brick of ceramic. When you allow a failed oxygen sensor to corrupt your Ford's fuel management system, the collateral damage ripples backward into the core of your engine. The manufacturer built these power plants with highly integrated systems, meaning a fault in one cheap component creates a domino effect that compromises critical mechanical tolerances. If you think you can just hollow out a melted converter or ignore the underlying cause of the failure, you are setting yourself up for an absolute mechanical catastrophe. We are digging deeper into the hidden engine settings, calibration blind spots, and secondary systems that this $8 sensor completely destabilizes when it goes sideways. We are continuing the countdown of the most critical failure vectors you must intercept before your powertrain is rendered completely useless. Sign number 0. The truncated short-term fuel trim limit. When an upstream oxygen sensor begins to fail or sends an inaccurate reading, the engine control module attempts to compensate using a software routine known as closed-loop fuel control. The computer monitors the sensor's voltage and alters fuel delivery via the short-term fuel trim, STFT. Under normal parameters, the STFT should modulate within a tight window of positive or negative 5%. However, when the sensor becomes severely degraded, the computer forces the STFT to its absolute maximum adaptation limit, frequently pushing past positive 25% extra fuel. Once the short-term trim hits this software ceiling, the computer can no longer adapt to real-time driving conditions like altitude changes or sudden throttle transitions. It loses its electronic safety net. The software hits a calibration wall, and the engine control module enters a defensive, fail-safe state. This locks the fuel injectors into a static, rich command map that completely bypasses real-time sensor feedback. The mechanical reality, when your engine management system hits its fuel trim limit, it stops acting as an adaptive computer and starts operating on generic, hard-coded values that completely overfuel the cylinders at idle, the actionable fix. Plug in your diagnostic scan tool and navigate to the live data stream for STFT and LTFT, long-term fuel trim. Add the two percentages together. If the total combined correction exceeds positive 15% at a hot idle, your upstream sensor is driving the system to its limit and must be replaced immediately. Half feature breakdown. The EcoBoost turbocharger thermal backfeed. If you drive a Ford equipped with a 2.7-liter or 3.5-liter EcoBoost engine, the danger of a failed upstream oxygen sensor is amplified exponentially by the presence of your turbochargers. On these specific twin-turbo platforms, the upstream O2 sensors are threaded directly into the exhaust manifolds, positioned mere inches ahead of the turbocharger turbine housings. When a failing sensor tricks the computer into dumping excessive fuel, that raw fuel does not just ignite in the catalytic converter. It begins detonating inside the exhaust manifold and the turbine housing itself. This localized secondary combustion creates extreme thermal energy right at the turbocharger bearings. The internal temperatures of the turbine housing quickly exceed the thermal limits of the engine oil feeding the turbo center housing rotating assembly, CHRA. The engine oil literally cooks inside the oil feed lines, turning into solid carbon deposits through a process known as oil coking. This completely blocks the oil passages, starving the turbocharger bearings of lubrication while they are spinning at over 150,000 RPM. The engineering reasoning, turbocharger shaft bearings require a constant, uninterrupted film of clean oil under pressure to prevent metal-to-metal contact. The extreme exhaust heat caused by an O2 sensor-induced rich mixture destroys the oil's viscosity and clogs the micro-passages feeding the bearing journals. The cost comparison. A proactive $30 OEM equivalent upstream sensor prevents an oil coking event that destroys both turbochargers, saving you from a grueling $4,500 twin-turbo replacement bill involving broken manifold studs and extensive labor. The actionable fix. For EcoBoost owners, do not wait for a check engine light. Inspect the metal oil feed lines leading to your turbochargers for discoloration or baked-on oil residue. If the lines look charred, replace your upstream oxygen sensors immediately and swap out the turbo oil feed lines and filters before bearing failure occurs, the silent killer. PCV system oil vapor contamination. Many vehicle owners blame the oxygen sensor itself for failing prematurely, but the root cause often traces back to an overlooked engine feature, the positive crankcase ventilation (PCV) system. Ford engines, particularly the modern direct-injected variants, generate significant crankcase pressure and oil mist. If the PCV valve sticks open or the internal oil separator baffles become clogged, heavy oil vapors are sucked directly into the intake manifold, bypassing the combustion process and blowing straight out into the exhaust stream. When these atomized oil droplets hit the blistering hot upstream oxygen sensor, they burn instantly on the outer protective shield and the internal zirconium element. This creates a permanent, glassy phosphorus and silica glaze over the ceramic sampling tip. This glaze acts as an insulative blanket, completely blinding the sensor to the actual oxygen content in the exhaust gas. The sensor is permanently tricked into reading a lean mixture, forcing the engine into the catastrophic rich loop we discussed earlier. The mechanical reality: you can change your oxygen sensor every month. But if your PCV system is actively migrating engine oil into the combustion chambers, the new sensor will be chemically poisoned and ruined within a few thousand miles. The actionable fix: every time you replace an upstream oxygen sensor, you must inspect the old sensor tip. If the tip is coated in a powdery white or light gray ash deposit, it indicates chemical poisoning from oil or coolant. Immediately replace your PCV valve and install an upgraded oil separator kit to protect the new sensor from premature contamination. The blind spot. Downstream sensor delusion. A common diagnostic myth among DIY mechanics is that all oxygen sensors are created equal and do the same job. This misconception causes people to waste hundreds of dollars replacing the wrong parts. Your Ford utilizes downstream oxygen sensors, which are located after the catalytic converter. When a vehicle owner sees a generic code reader display an O2 sensor circuit fault, they often buy the cheapest, easiest to reach sensor on the exhaust pipe, which is almost always the downstream unit. This is a critical diagnostic failure. The downstream sensors have absolutely zero control over your engine's real-time air-fuel ratio calibration. Their sole purpose in the factory software is to act as an emissions hall monitor, checking whether the catalytic converter is doing its job by measuring oxygen storage capacity. If your upstream sensor has failed and is actively melting your converter, the downstream sensor will eventually trigger a catalyst efficiency code, P0420 or P0430. If you make the mistake of replacing that downstream sensor, you have done absolutely nothing to stop the engine from running rich and continuing to melt the exhaust system. The economic framing. Misdiagnosing the system and replacing a $60 downstream sensor does nothing to fix a rich engine condition, resulting in the total loss of that new sensor when the melting converter sends ceramic shrapnel down the tailpipe. The actionable fix. When reading diagnostic trouble codes, always look specifically for the bank and sensor number designations. Sensor 1 always refers to the critical upstream sensor before the converter, while sensor 2 refers to the downstream monitor. Never replace a sensor 2 unit expecting to fix a rich running engine performance issue. The most infuriating part of this entire mechanical design flaw is that the factory instrument cluster is programmed to protect the manufacturer's emissions rating before it protects your engine hardware. The check engine light is often delayed from illuminating until a fault has occurred consistently over multiple driving cycles. By the time the electronics finally decide to illuminate that amber warning light on your dashboard, the physical degradation of your exhaust valves, turbocharger bearings, and catalytic substrates is already well underway. You cannot afford to rely on a reactive warning system that is calibrated to let components degrade to the edge of failure before alerting the driver. If you think that a simple sensor swap is the end of the maintenance cycle for a high-mileage Ford platform, you are completely ignoring how these engines adapt to new parts. We have uncovered how a degraded upstream oxygen sensor blinds your engine control module, cooks your turbochargers, and melts your catalytic converter into a solid block of fused glass. But we have not yet touched the most deceptive, financially ruinous trap hidden within Ford's factory engine management logic. The software engineers built a silent calibration blind spot directly into the vehicle's long-term memory. It is an algorithmic flaw that lies completely dormant until you try to fix the vehicle. If you install a brand new sensor without knowing how to force the computer to erase its historical operating data, you can instantly inflict catastrophic mechanical damage on a fresh set of components during your very first test drive. We are closing out this countdown with the ultimate failure modes that catch even professional technicians off guard. Sign number -1. Long-term fuel trim memory lock. The single most deceptive feature on a modern Ford vehicle is the long-term fuel trim, LTFT, non-volatile memory cell. When your upstream O2 sensor spends months slowly dying and reporting an artificial lean condition, the engine control module does not just add fuel in the moment. It permanently alters its baseline volumetric efficiency calculations, writing a massive fuel multiplier into its long-term adaptive memory registers. This LTFT profile is saved in a type of computer memory that does not simply vanish when you turn off the ignition key or unhook the vehicle's negative battery cable for a few minutes. when you unthread that dead carbon-coated sensor and screw in a brand new, hypersensitive $15 replacement, you might think the job is done. It isn't. When you start the engine, the brand new sensor instantly begins delivering accurate, high-voltage readings, signaling that the engine is running incredibly rich. However, because the computer is still applying its historical, corrupted long-term memory multiplier, it continues to pulse the fuel injectors at maximum capacity. The mechanical reality. The engine control module enters an algorithmic conflict loop. The new sensor reports an extreme rich condition, while the old memory profile commands massive fuel delivery. This causes a massive fuel spike that can wash oil off the cylinder walls in minutes, inducing severe piston ring friction and immediate catalytic overfiring on a vehicle that was supposedly fixed. The actionable fix. Do not simply change the part and drive away. You must use a diagnostic scan tool to access the PCM Special Functions menu and execute a hard fuel trim reset or CAM, Keep Alive Memory, Clear. This forces the computer to wipe its corrupted historical adaptations and build a fresh baseline USI. NG, the accurate data from your new sensor. Hider feature breakdown. The direct injection bore wash and oil dilution crisis is the absolute apex of structural engine damage caused by a failed upstream sensor on modern EcoBoost and TI VCT engines. These power plants utilize gasoline direct injection, GDI, where fuel is sprayed directly into the combustion chambers at pressures exceeding 2000 psi, rather than being mixed with air in the intake ports, when a failed oxygen sensor commands an unyielding, maximum-rich fuel map. The injectors spray an excessive volume of liquid gasoline under immense pressure directly onto the aluminum piston crowns and iron cylinder liners. This phenomenon is known as bore washing. Liquid gasoline is an exceptionally effective solvent. It instantly strips away the microscopic, cross-hatched film of motor oil that lubricates the boundary layer between your piston rings and the cylinder walls, without that critical oil film. The metal piston rings scrape directly against the bare cylinder walls at high speed. This creates severe micro-welding, scoring, and deep gouges in the engine block engine bores. The engineering reasoning. The structural integrity of an engine's compression sealing relies on a fluid barrier measuring less than 1/100th of a millimeter thick. When excessive fuel delivery dissolves this fluid barrier, combustion blow-by gases force their way past the unlubricated rings, pushing vaporized raw gasoline directly down into the oil pan. The structural consequence. Your engine oil becomes heavily diluted with raw gasoline, severely dropping its viscosity from a protective 5W30 down to the consistency of water. Your oil pressure plummets at hot idle, starving the overhead camshaft journals, variable cam timing, VCT phasers, and main crankshaft bearings of essential lubrication. The cost comparison. Neglecting an $8 to $15 upstream oxygen sensor allows cylinder bore washing and oil dilution to progress until the engine throws a connecting rod through the block, turning an easily preventable maintenance item into a catastrophic $8,000 long block engine replacement. The actionable fix. Pull your engine oil dipstick and smell the oil directly. If the oil possesses a strong, pungent odor of raw gasoline, or if the fluid level on the dipstick reads significantly above the full crosshatch mark, your upstream sensor has already compromised your fuel trims. Replace the sensor immediately. Perform a complete engine oil and filter flush, and do not drive the vehicle until clean, undiluted oil is flowing through the passages. The final actionable blueprint. Compounding your protection, you cannot rely on manufacturer defaults to protect your automotive investments. To ensure your Ford engine never falls victim to this cascading loop of exhaust and structural destruction, you must execute a strict, proactive maintenance protocol. Let's review the entire operational diagnostic blueprint that saves you thousands of dollars in unneeded garage bills. Maintenance Vector Diagnostic Indicator Actionable Countermeasure Expected. Part Cost Upstream O2 Sensor VO. Litage Lag 1 second. Lazy Switching Waveform Proactive Replacement at 80,000 miles using specialized O2 socket $15. $50 OEM equivalent. Fuel trim alignment combines TFT plus LTFT values exceeding plus 15%. Executed a hard cam clear via scan tool to wipe historical adaptive maps. Using DIY OBD2 tool, oil migration white or light gray ash glaze on old sensor tip. Replace. PCV valve assembly. Install an inline oil separator system. $20 and $120 lubrication integrity gasoline sen on dipstick. Elevated engine oil level, immediate oil and filter change, post-sensor replacement, check hot oil pressure. $40. $60 stop waiting for a yellow light on your dashboard to dictate when you care for your vehicle. The factory programming is configured to prioritize corporate emissions compliance over the long-term structural life of your internal engine components.